basic constitutive laws. Now, this is not a course in elasticity or material properties, but we need to recognize that rocks are complicated. And some rocks, like this strong carbonate sample, which is being deformed, a cylindrical sample being deformed by an axial load in the laboratory, we see a little bit of inelastic or nonlinear behavior as we first begin to apply a load to it, cracks start closing. Then we see a long range of elastic behavior. And then eventually, as we get close to the strength of the rock begins to fail, and ultimately it fails. And so, this rock is pretty elastic, right? And it's pretty linear, and it's pretty good. But that's just sort of one end member. And we can derive various constitutive laws to describe these kinds of behavior. So I just showed you a fairly realistic, strong rock, which might be idealized as a linear, elastic, simple system. And that might be good enough for some problems for those kinds of rocks. However, when you introduce pore fluid into a rock, suddenly everything becomes more complicated. For example, the pore fluid in a porous sedimentary rock has the capability of supporting the externally applied stresses when those stresses are applied quickly with respect to the permeability. In other words, think about a tennis ball, which has got a little pinhole in it, and you've somehow filled up that tennis ball with water. If you deform that tennis ball slowly, the water just sort of squirts out, and the tennis ball is not very strong. If someone actually threw that tennis ball against the wall, when it hit the wall, it'd be like throwing a rock against the wall. Because the pore fluid pressure, right, the pore fluid pressure would go up fast. It can't get out because of that tiny little pinhole, and therefore the stiffness of that tennis ball is greatly increased. So now the elastic modulus, the stiffness, depends on the rate at which it's being loaded. And so if you load a sample fast, it appears very stiff and strong. If you load it slowly, it appears very compliant. Or if you're passing seismic waves through the rock, high-frequency waves would see a very stiff rock, and very low-frequency waves would see a very soft rock, and this is called dispersion, the fact that waves of different frequencies will see different velocities or be sensitive to different elastic moduli. And so we go from a simple linear elastic system, the minute we add pore fluids, life becomes a lot more complicated. In an elastic plastic rock, which can be conceptualized by a spring pulling a block, the relationship between displacement and force will go up linearly. The slope will be the spring constant. But at some point, that block will start to slide. And then you get lots of displacement at a constant force. Okay? So it's elastic, and then it's plastic. Okay, lots of irreversible deformation, because if you back off that force, right, the block doesn't slide backwards. You still have this, permanent deformation. So it's elastic, plastic, and we actually see that in kind of softer rocks. You begin to deform them; they start to they start to deform. So you deform them a bit, then you unload them in the lab, and you'll have a net force that's left behind. And finally, you've got a viscoplastic or a viscoelastic or a viscoplastic rock. These are rocks which the rock intrinsically, outside the role of pore fluid pressure, okay, this rock could be dry, but intrinsically its deformation is time dependent. And this actually turns out to be very, very important in a wide variety of materials, and we'll spend some time talking about viscoelastic and viscoplastic properties. So as we describe rock behavior mechanically, it's sometimes going to be okay to use simple elastic models or the rock is elastic to the point of failure. And once it starts to fail, obviously, it's inelastic, okay? And that's not going to be a bad assumption. And in other cases, we're going to be very, very cognizant of the fact that the rate at which the rock is loading is going to be very important in determining how the rock responds. And we'll work through some of the mathematical laws that are associated with each of these cases. Rock strength, you know, many decades of laboratory research have been done. We can describe strength in many different ways. We're going to divide this discussion into kind of compressive strength, not only what it is, how we describe it, what laws we use, what strength anisotropy is, obviously flaws in rock. You can think of bedding planes in shale, right? Make shales intrinsically, make the strength of shales intrinsically anisotropic. Compaction, rocks failing under kind of a mean, effective, confining stress. You might think about it as a rock just compacting as it's being buried during burial and diagenesis, or the fact that a weak rock is stable, but when you start producing the fluids, the effective stress goes up and then the rock begins to compact. And the third mode of failure that's important, of course, is the tensile strength of rock. While the tensile strength is very low and is typically negligible, we want to talk about hydraulic fracture propagation, and we want to keep tensile strength in our minds because of that. Another thing we talk about in Chapter 4 is shear strength, the strength of faults. And this is important whether we're trying to understand how to predict whether a fault will slip. For example, if we're injecting fluid, okay, or we're somehow changing the stress field, is a fault going to slip? But it's also of first order importance in understanding stress magnitudes in the crust. Now, if we think about the forces in the crust in a geological context, right? Plates are moving, geologic processes are active, stresses are being transmitted through the interiors of continents. Those stresses can accumulate, but they can't accumulate beyond the strength of pre-existing faults in the crust. And when we have pre-existing faults in the crust, the stresses that are arising over, geologic time will suddenly stop increasing because those faults will start sliding. So this concept of understanding shear deformation on pre-existing faults is going to be very important at a reservoir scale for understanding the faults in the reservoir. When we start talking about the problem of triggered seismicity, they're going to be very important, and they're going to be of first order importance. And when we first start talking about what are the stresses in the earth, what are the stress magnitudes, we have to recognize that geologically the Earth's crust is in a state in many places of sort of failure equilibrium, and whether it is or not, the strength of pre-existing faults are always going to limit the magnitudes of stresses that exist. So these are very important principles that are discussed in the latter part of Chapter 4. Chapter 5, and that's what I illustrate here, where I take that same diagram I showed you before, but we will derive some simple formulas, and we will demonstrate that in a normal faulting situation, even though we know that the minimum stress is greater than the pore pressure, it's less than the vertical stress, it can only go so low, right? That red dashed line represents the minimum value of SH min, because if it gets any lower, normal faults will start to move. So now we've really established a range of stress magnitudes at a given depth, knowing that it's normal faulting, knowing what the pore pressure is, and knowing that not all values of stress are allowable because the Earth just can't hold all values of stress. In a normal faulting environment, there's a lower limit on the magnitude of the least horizontal stress. Similarly, in a strike-slip faulting environment, if we know the value of the minimum horizontal stress, we can say what the upper bound of the maximum horizontal stress is. So the anisotropy between the two horizontal stresses is bounded by the strength of the crust. In a reverse faulting regime, the bound on SH max is really quite high, and we can get very, very large stresses in situ. And in the cases we'll be working on, pure reverse faulting is relatively rare, but nonetheless, understanding that the faulted crust provides a fundamental constraint on stress magnitudes will give us a very important conceptual tool to build stress models. And when we don't have perfect information, to at least put some bounds. We can say, okay, well, we don't know what SH max is exactly, but we know it can't be any larger than a given value. And SH max is by definition always going to be larger than SH min, and it can't, if we know SH min, which we typically get, from hydraulic fracturing, we know SH max lower bound, and we know SH max is upper bound. And for example, if you're working on a problem of wellbore stability or fault slip, you can just investigate both of those bounds. While you don't have precise information, you've got bounds to work under, quantitative bounds. Okay, faults and fractures are important because the Earth comes to you with a lot of baggage, tens of millions or hundreds of millions of years of deformation. There are many fractures and faults that have been introduced over geologic time. Now, in the current stress field, or the stress field that existed at the time fractures and faults were active, you can relate, and we will talk about this, the stress state to the orientation of the fractures and faults that are of most importance. Okay? So if we go through geologic time, and as different processes occur, we could try to, in fact, reinvent the distribution of fractures and faults that we see. Or, fortunately, this is the case, we can say, okay, we know there are a lot of fractures and faults, but we know that today we have a strike-slip faulting regime. And so what we know is that despite what's in the rock, we know which subsets of the faults, which in this case would be near vertical faults, which are kind of conjugate around the direction of maximum horizontal stress, about 30 degrees either way. We know which faults are potentially active in today's stress field. Okay? So we're going to go through that, trying to understand the difference between what's in the rock and what's been inherited over time to what subset of those faults are the ones that are potentially active today. Right? We're interested in that because we want to know if they're potentially going to slip, and we're interested in that because the ones that are potentially active today are going to be the ones that are most important for fluid flow. Okay? So this idea of relating the stress field to the faults, so that now we've related the stress field to the pore pressure, and we've now relating the faults to the stress field, and so you can see how all of these various things are interrelated as we build our model. So how do we get our information about stress? We use the stress concentration around the vertical well. We'll go through the mathematics for this in great detail, but basically the way to think about it, we're going to go through it all for a vertical well where one principal stress is vertical. That is sort of the normal case where one principal stress is vertical. Vertical wells are ubiquitous, but we're going to then generalize it for the general case of any orientation of any well, and in fact any orientation of any stress field, which is an unusual case, but a case we'll talk about in the next lecture. For a vertical well where one principal stress is vertical, the hoop stress, the stress that acts sort of in parallel to the circumference of the well, this hoop stress varies sinusoidally around the well, such that, in this case, if we have SH max operating in sort of a north-south direction, we see a very strong compressive hoop stress, 90 degrees from the direction of SH max, which can lead to wellbore failure, compressive failure of the rock, and these are called breakouts. The rock here fails and falls out during the drilling process. Under some conditions, this hoop stress can actually become negative, and the rock can actually fail in tension. These are called drilling-induced tensile fractures, and this can also occur during normal drilling operations. Now, because the stress concentration is related to the orientation of stresses, if we know the orientation of the breakouts or we know the orientation of the drilling-induced tensile fractures, we know the orientation of the stress state. We also know that the stress concentration here was enough to exceed the strength of the rock. So just by recognizing that these failures of the rock have occurred, we're beginning to get a lot of information about the stress field just by looking at the well. And here's what looking at the well means. Now on the left is what's called a UBI log. It's an ultrasonic scan of the wellbore wall. So this is a few meters of depth, and we go around the wall from around the well, north, east, south, west, and north. And here we make a cross-section of the well from these little acoustic pulses that have been bounced off the wall, and we can in fact see the breakouts here, which correspond to these dark zones here where the acoustic pulse is scattered. And immediately we know that the SH max direction is like that. Okay. Now this is an electrical image log. We'll talk about this more. It's Schlumberger, one of the service companies, refer to these logs as FMI logs. It's basically an array of electrodes pushed against the wellbore wall. And what you can see is this out of focus zone here, and that's because this array of electrodes is not in good contact with the wellbore wall here. But nonetheless, you can see the result of these breakouts occurring. And again, it gives you an idea of SH max. What's interesting about this well is here and here, we actually see drilling-induced tensile fractures, which are 90 degrees from the breakouts, right? This is north, east, south, west, north. So these two things are 180 degrees apart, and these two are 180 degrees apart and 90 degrees offset. So those drilling-induced tensile fractures, which you can't see in the cross-section here, are giving us an independent indication of the direction. And again, it's telling us that the hoop stress actually got down into a tensile failure mode, and that the compressive stress got into a mode where we're actually exceeding the strength of the rock. Just by looking at the well, we're learning a lot about the relationship between stress in the earth and the rock properties.